A ball is launched horizontally from the edge of a cliff of height h with an initial speed v0. Ignoring air resistance, determine how far from the base of the cliff the ball lands in terms of v0, h, and g. So to solve this problem, let's start with one of our constant acceleration kinematic equations. So this one says that the displacement is equal to the initial velocity times the time t plus a term due to acceleration, which is 1/2 at squared. So let's take this and apply it in both the x and y directions. So here I've defined a coordinate system with x pointing towards the right and y pointing upwards, positive y pointing upwards. The origin, let's call the origin here. So this point is the origin. It's going to be at the base of the cliff where the ball is launched from. And we want to find how far it lands. So let's apply this kinematic equation to both the x and the y directions. So in the x direction, we have that the displacement in the x direction is just v0 times t. And here, instead of the displacement, I'm going to use the letter d to make this less confusing. So it ends up, the ball launches and it lands some distance d away. And this d is our displacement. And delta x is really d minus 0 in this case, which is just d. And now let's apply this equation to the y direction. So we have that the displacement in the y direction is equal to the initial velocity in the y direction plus 1/2 times the acceleration in the y direction. So the initial velocity in the y direction is 0 because it's launched horizontally, so this term disappears. And ay, the acceleration in the y direction, this is just negative g, since it's accelerating in the negative y direction. And the displacement of y is just the final y position minus the initial y position. The final y position is 0, and the initial y position is h. So putting all of this together, we can simplify this to say that negative h is equal to 1/2 times negative g times t squared. And the negatives cancel. And so now, if I clean this up a little, our second equation is that h equals 1/2 gt squared. So now we have two equations, and we want to solve for d. So ideally, we notice that we have a t in both equations. So we can solve for t in terms of these constants here, which we were told to express our answer in, and eliminate t from both equations. So let's do that. And if we do this, if we multiply both sides by 2, divide by g, so 2h over g, and then we square root it to get that t equals square root of 2h over g. And then we plug it back into our first equation. So d is v0 times t, which is v0 times the square root of 2h over g. And this would be our answer. But we can also run a few checks to make sure that our answer is sort of on the right track and not definitely wrong. So let's check the dimensions of both sides. So if this equation were true, then the units of d would have to be the same as the units of this quantity here, since they're set equal. So the units of d are just meters. It's a distance. And now what are the units of this quantity here? So let's figure that out. So v0 is a speed. So it has units of meters per second. In this case, it's some distance per second. And then inside the square root, 2 is just a number and it doesn't have a unit. H has units of meters. And in the bottom, we have g, which is an acceleration. So it has units of meters per second squared. So notice that the meters cancel out, and this becomes meters per second times the square root of 1 over 1 over second squared. So this just becomes the square root of second squared, and this becomes meters per second times second, which is just meters. And this does check out with d. So our dimensions are correct, and that gives us more confidence in this answer. So now one more thing that we can do is that we can check limiting cases. So perhaps we want to see what happens when, say, h approaches 0. So if we look at our expression as h approaches 0, this whole term approaches 0. So d approaches 0 as well. And this makes sense. If you shorten this cliff to like almost 0, then you're not really going to travel very far. So that does make sense. And we can also check what happens as, say, v naught approaches 0. And notice in this equation, as v naught approaches 0, this becomes very small, and this whole term becomes very small. So again, d approaches 0. And this again makes sense, because when you have a very small velocity, you're not going to get very far either. So that checks out. And as h increases, if we increase h, this whole term gets bigger, and so d increases. And so this does make sense. If you raise the height, the ball will probably fall for longer and therefore will go further. And one more thing, we can check what happens if g, the gravitational acceleration, increases. Well, if g increases, this denominator gets bigger. So this whole term ends up getting smaller. So d will decrease. And if you think about it, increasing the gravitational acceleration will cause it to fall down and hit the ground faster, reducing the time of flight and therefore reducing the distance. So this also makes sense. So these are just some checks you can do, and this is why you should also leave your answers, solve for your answer symbolically first, so that you can perform these checks and make sure that your answer actually does make sense in these certain cases. And it turns out that this is the correct expression for this problem. And that is how you would solve this problem here.